Carboxylic acids have the suffix oic acid. Okay, so for example, in this molecule here, we have 1, 2, 3, 4 carbons in the parent chain. All right, so for 4-carbon alkane would be butane. This now becomes butanoic acid. Okay, so you just stick that suffix on a lot like aldehydes. One of the convenient things about carboxylic acids is that they always have to be located on a terminal carbon. So they're always going to be located at position 1 on carbon 1. So we'll start counting from there. Let's do this next example, but notice that this has an alcohol group in there as well. So we need to take a look at this priority chart real quick before we can actually name this compound. We're going to be talking a lot about carboxylic acid derivatives. That would be like esters, acyl halides, amides, nitriles, but we will get to all of that. So for now, we're going to go ahead and ignore this portion of the chart. We'll cross that bridge when we get there. But notice that carboxylic acids are now our highest priority functional group. Okay. When we started the semester, we were over here at alcohols, and then we added some more functional groups. Carboxylic acids are the highest priority functional group we're going to learn about in this course, actually, which are a lower priority group. So instead of referring to that alcohol group with the "ol" suffix, we're going to use the hydroxy prefix. Okay, so let's go back to this example here. Besides that, the nomenclature is just like always, right? I'm going to find my parent chain. So I'm going to start here, 2, 3, 4, 5. So then I have my hydroxy is at position 5. Oh, and again, importantly, I'm going to start numbering from that carboxylic acid carbon. Okay, so this would be 5 hydroxy, 4,4-dimethyl pentanoic acid. Okay, so again, keep this priority list in mind. We'll cross the, that reds or the green stuff that I crossed off. We'll get there when we get there. I'm not going to make you guys memorize them. I'm going to focus way more on the IUPAC naming scheme and making sure that you know how to, generate the name of any miscellaneous compound you're given. I'm not big on memorizing common names. Got to be one exception though, and that is the all-important acetic acid. Okay, this, right? If we're going to be systematic, there are 1, 2 carbons. So this is ethanoic acid. You will literally never see ethanoic acid anywhere. It has acetic acid is just so important, such a deeply enrooted common name. I bet it's actually officially the IUPAC name, despite the fact that it doesn't have that same sort of whatever. So anytime you're about to write ethanoic acid, you instead put acetic. Okay, ethanoic doesn't exist, replace it with acetic. Okay, there are some other ones, formic acid, propionic. Notice how this is not propanoic, but the common name is propionic. This is not butanoic, the common name is butyric acid. I have no idea why. They're very commonly used. For the purposes of our course, we're going to stick to the IUPAC, the propanoic, butanoic, again, with the exception of acetic acid. We just got to know because that is just so commonly ingrained. Dioic acids or dicarboxylic acids. So kind of what we would expect, right? Similar to aldehydes. Again, they both have to be at the terminal end. So we don't actually have to specify the location. We just have to 1, 2, 3, 4, 5. Figure out how many carbons we have in our parent chain. Again, this would be, instead of just pentandioic acid, it's pentane dioic acid. The real reason they do this is so that you don't have 2 consonants sticking next to each other. So you just stick that E on there as well. So this is pentane dioic acid. And again, notice that we don't have to specify locations because we know they're just going to be on either end of this parent chain. All right, so now let's introduce the carboxylic acid derivatives. They're going to be a big portion of this particular chapter. What do I mean by that, right? So these are the various carboxylic acid derivatives. Okay, And notice the analogy here. I have this carboxylic acid, but instead of having an OH group, that hydroxy group, this is going to be replaced with various other heteroatoms, okay? So if it's a halogen, we call it an acid halide, or actually what I call it for whatever reason, how I learned it, same exact thing, no difference. So whatever you guys want to use is an acyl halide, okay? So that's what that heteroatom is, not that hydroxy group, but now a halogen. Acid anhydride. This is like if this portion here was replaced with a carboxylate ion, or rather carboxylate group, right? So they're almost like two carboxylic acid groups attached to the same oxygen. So it's called an acid anhydride. An ester. Now we have, instead of the hydroxy group, it's now an alkoxy group. And lastly, the amide, IDE, is when there is a nitrogen as that heteroatom, right? So don't mix this up. This is not an amine, which is when you would have that nitrogen all by itself. But when there's that carbonyl carbon right next door, it's called an amide. And another functional group which doesn't quite look as cookie cutter similar as these other ones, but we can kind of lump into the same category, is a nitrile group. It behaves very much the same way because you have that carbon that has 3 bonds to other electronegative atoms. So we're going to see that the nitrile group behaves very similar to our other carboxylic acid derivatives. The acyl halides and the anhydrides are relatively unstable, so you don't find them very often in nature. However, that makes them great for synthetic chemistry, right? So they're very reactive, meaning that we can start with them and generate go a lot of different paths. So they are actually quite powerful. Esters and amides are very abundant. Esters tend to be the good smelling compounds that we see that are found in all of nature's flowers and fruits. Your lab, right, you synthesize this isopentyl acetate, which is naturally found in bananas. And then amides are like one of the building blocks of nature, in that they're the key bond that you're going to find in proteins and in enzymes, okay? Anyway, all these things are found kind of all over these things. They're really what nature uses. So what we're going to do is, right, these are carboxylic acid derivatives. So you can sort of think of, oh, I start with my carboxylic acid name, but instead of ending with oic acid, I'm going to end with oil halide. And not just halide, but you're going to end with your specific halides. So fluoride, bromide, iodide. We're actually going to see that the acyl chlorides are the most sort of common, but all right. So for example, here I have my 1, 2, 3, 4 carbon carboxylic acids. So that would be butanoic acid. But again, instead of the oic acid, I'm going to use oil chloride. So this is butanoil chloride. Likewise over here, 1, 2, 3, I have a methyl on carbon 2, right? Because this always has to get carbon 1. So 2-methyl propanoic acid. But again, instead of having that oic acid, when I go over to my acyl halide, I'm going to use the oil, and in this case, fluoride. So this is 2-methyl propanoil fluoride. Okay. Acid anhydrides. We're going to sort of only touch a small subset of the acid anhydrides, and that is the symmetric ones. Okay. But what we're going to do is we're going to just name it as if it was our carboxylic acid, but instead of using the word acid, we're going to use the word anhydride, right? So Simple example, acetic acid becomes acetic anhydride. And yes, notice that it is symmetric on either side of that oxygen. Both halves would have been the acetic acid half. So then over here, we have 1, 2, 3, 4, 5, 6 carbons. So this is hexanoic acid. Well, now we get to the analogous acid anhydride of, of this carboxylic acid derivative. This becomes hexanoic anhydride. Just notice that if you had one of those special common named acids, you could do the same thing. So succinic acid becomes succinic anhydride when you link it together. Esters. All right, so now we're going to talk about ester nomenclature. This is maybe one of the more difficult ones because you have like these two portions of this functional group. And let me show you what I mean by that. So again, you're sort of going to try to, in your mind, start with your carboxylic acid derivative and then modify it. In this case, we're going to drop the oic ending and replace it with O8. But now we also have this portion of our ester to worry about, right? Because that could have been any length long. That obviously has to be accounted for in our name. So out front, you're now going to stick some sort of a prefix on there that's going to correspond to how long, how many carbons that portion of your ester is. So it would be acetic acid. Now this becomes ethyl, referring to that half of the molecule, and then acetate, which refers to that 2 carbon portion on the back half. Okay, so let's start over here using, again, got to include these because they're going to be on Wiley and stuff. Let's start with, sort of one of these here and do how we our systematic naming. So the first thing you're going to do is you're going to chop these molecules at this carbon oxygen bond, not this one and not this one in particular. Okay, so just make a note of that. Your single bonded oxygen carbon bond. The reason is because this back half is going to be considered our parent chain. Okay, notice how it contains that sort of carboxylic acid derivative portion. It's got the carbonyl carbon, it's got the oxygen. Okay, this parent chain has 1, 2, 3, 4 carbons. That means that if it was a carboxylic acid, it would be butanoic acid. Instead, we're going to drop the oic acid and put O8. So this is butanoate. Okay, that takes care of the parent half. Now I'm going to look at the substituent half, which is everything else. And that consists of 1, 2, 3, 4, 5 carbons, meaning that this is pentyl butanoate, 2 separate words. We're not used to seeing spaces in our nomenclature, okay? Esters are an exception to that. And that's because we're referring to these 2 chunks of this molecule in different portions, okay? Notice that it didn't matter which one was longer, right? It didn't matter that my substituent half, the green half, was longer than the half. It all mattered where I cut, which was a single bonded oxygen carbon bond. And that was to keep that parent half as that carboxylic acid derivative. Let's do another example here. So everybody take a second. Tell me where I'm going to cut in this molecule to generate this nomenclature. All right, I'm going to cut at this bond here. This half is my parent chain. And this half is my substituent, my sort of prefix, the thing that's going to go out front. Now you just name these 2 separately, and notice that there are sort of these branched functional groups, alkyl groups, methyl groups off there. Just pay attention to how we name it here. So in each chunk, you're going to find the parent chain. 1, 2, 3. You're always going to start numbering from that functional group, from that ester functional group. So this gets to be carbon 1, this is carbon 2, this is carbon 3. So my parent chain is 2-methyl. It would be propanoic acid if it was the carboxylic acid, but since it's an ester, I'm going to change that to propanoate. Okay, now I need to go and do the substituent half. Again, I'm going to have to find my parent chain. 1, 2, 3, 4 carbons long. And again, I'm going to number from the ester functional group. Okay, so this carbon here has to be carbon 1. Don't start numbering from the other end of the molecule. Number from what's closest to the ester functional group. 2, 3, 4. So this would be 3-methyl. Then 4 carbons long would be butyl, space 2-methylpropanoate. Okay, so this, notice how I kept those alkyl groups, those methyl groups. One was kept in that substituent portion of the molecule, right? This is everything in the green box is accounted for in that. And everything in the blue box is accounted for in that. Amides, right? Different from amines. Again, just to stress, amides. You're going to replace the oic acid with amide. So that's kind of nice, makes it easy. Again, so if we're going to take acetic acid as an example, it goes from acetic acid to acetamide. Again, kind of more focused on the IUPAC nomenclature here. Here's my parent chain. If it was carboxylic acid, it would be the 4 carbons butanoic acid, but now it's butanamide. Notice how you got to keep that AN in there, right? Because if I had a double bond here, that would have been butanamide. Okay. Butanamide. So now, kind of like esters, amides can have any sort of length of carbon coming off of that nitrogen. So how do we account for that? Well, similar to what we did, we're going to kind of think about it. We're going to cleave at this bond here. Okay, that's going to be the back half that we're going to worry about naming differently. We're going to do a little bit different than what we did before, but nonetheless, this is sort of my parent. Again, I think 1, 2, 3, 4. Yep. So this is a, butanamide. But now I got to account for that methyl group off of the nitrogen. And this we do a little bit different than we did with esters. We're going to sort of include it as if it were on any other carbon. Instead of number, we're going to indicate where it is with the letter N. So this is N-methyl, no spaces, butanamide. Right, so just like if I had a methyl group coming off of carbon 2 right here, this would have been 2-methyl. When it's coming off, well, that was not how you spell methyl. When it's coming off of the nitrogen, it's N-methyl. And you treat that N just like it were any other sort of number. By that, I mean, you're going to put that methyl in alphabetical order with all the other prefixes. Let's do the next example here because this will be a good one. So again, I'm going to identify my parent chain. Number my parent chain, 1, 2, 3, 4. Notice I have a methyl group coming off of carbon 3. But I also, so that's what this is, but I also have a methyl group coming off of the nitrogen, an N-methyl group. And then lastly, I have an ethyl group coming off of my nitrogen. So you treat these just like every other prefix. What's going to come first is alphabetical. So that will be my N-ethyl. And then 3N-dimethyl. Right, so just like if it was on, if I had a methyl group there, it would be 2,3-dimethyl, we sort of treat it the exact same. This is 3N-dimethyl. Butanamide. Okay. With the common or with the IUPAC names, it's not O-nitrile. You actually keep the E from the ane, ene, or the ine. So what do I mean by that? Let's just look here. So here you figure out how many carbons you have in your parent chain. 1, 2, 3, 4, 5. So this would be pentane, whatever would have been how we started, but we're actually going to keep that E as well. Pentane nitrile. Likewise, if we have this one where we have 1, 2, 3, 4, 5, 6 carbons in our parent chain. Again, I'm going to have to make sure to number starting with that nitrile group. 1, 2, 3, 4, 5, 6. So this would be 5-pentene nitrile or pent-5-ene nitrile. Either would be accepted. Again, notice that I'm keeping that EN there because otherwise, like in this case, you can see I'd have two N's running into each other. So that's when we include the E, is when you're going to have two consonants otherwise jetting up against each other.